having me here. And thanks for the introduction. And let me put it full screen. You can see the which screen are you looking at? So it's a full screen or the presenter's mode?
It's presenter's mode.
Okay. How about this one?
No, now it's full screen.
Okay, that's good. Hi everyone. I'm very happy to present our work, iClear work here. My name is Wuyang Chen. I'm a PhD student in UT Austin. And our iClear work names the neural architecture search on ImageNet in 4 GPU hours, a theoretically inspired perspective. So I know that this talk, this whole series of talk is mainly about AutoML. So I think that this work is very relevant to this series of talks, and I hope that everyone can be beneficial from my talk and our work here. So the AutoML work I specifically talk about is about neural architecture search, and so neural architecture search is about searching for a specific architecture. One second, let me make my pointer always visible here. You can see my pointer, right? Can everyone see my pointer?
Yes.
Oh, okay, cool. So neural architecture search is about finding an optimal architecture in a given search space. So for example, this search space is designed by Xuanyi Dong, who I think who gave the talk last time here in his work NAS-Bench-201. For example, we have the search space for both the topology of the network and also the operators for the network. And we want to find out a single path with some specific operators that can perform the best accuracy on either CIFAR or the ImageNet dataset. And previously, we know that neural architecture search heavily counts on the architecture evaluation. So basically, the neural architecture search is an optimization problem. And at each sampling point, we want to investigate how good the architecture is. So so it means that we have to find some approaches to investigate the performance or the loss values of the current sampled architecture. Currently, there are two mainstream in doing this evaluation. One is the training-based neural architecture search, and the other one is the predictor-based neural architecture search. So the training-based, including the weight sharing approach, the reinforcement learning or evolution, they are I count them all into the training-based neural architecture search because they have to design some proxy tasks to evaluate the architecture, and this proxy task requires a gradient descent. For example, some early stopping and truncated architecture or truncated data set, something like that. And the other approach is a predictor-based, which means that we first probably have a bunch of trend converged architecture, and we know their ground truth accuracy, and we train a predictor network of something like the graph neural networks, and try to use this predictor to predict the unseen architectures in the future search. So that means that both these two approaches involve training in their evaluation, and we know that the architecture's training itself is slow and requires high computation cost. And also, if we want to reduce this computation cost, we may want to train in a very few epochs, which may cause the evaluation unstable. And so there are two core questions in our work. So first is how to optimize the NAS at networks in initialization without any training. So if we can do this evaluation at initialization, then the whole cost of the neural search can be dramatically reduced. And the second question is that can we define how to evaluate NAS by analyzing the trainability and the expressivity of the architecture, which I will include the more details in the next few slides. But the high-level idea is that if we can evaluate the architecture just by analyzing their properties without any training, so this second question will help us solve the first question. Please stop me anytime if you have any questions. So let's take a look at the core part in our work. So how to analyze the network's trainability and expressivity, especially at initialization. So first, we need to define what is the trainability and the expressivity for the new architecture. So the trainability indicates how well the network can be optimized by gradient descent. Some typical examples that a network cannot be well optimized by gradient descent are any gradient vanishing or explosion during the training, or any overfitting to the training set, or some easy classes, for example, in the long tail problem. So these two problems are quite often observed in our problems, especially some early design architectures where the training by gradient descent itself is relatively hard. Um, and for the expressivity itself, is more easier to understand because whatever task or network we are training, we are essentially try to approximate the ground truth function defined by the task by training the network. So that means if we are dealing with a very hard task, we are expecting that our network can have the capability to approximate that complex function defined by the task. So the bottom line is that we are expecting the network have the capability to approximate any complex functions. And here I give a very popular example, and I think that many of us has experience in that. For the trainability itself, the ResNet probably has better trainability than VGG because we know that the ski connections significantly ease the training itself. And VGG, we know that for some complex tasks like the segmentation or detection, VGG has even have to leverage stage-wide training, which is very hard and difficult. And for the expressivity itself, we know that many of the VGG networks have larger amount of number of parameters than ResNet. So ideally, the VGG network can represent more complex functions than ResNet. But by combining these two notions, we can see that simply considering trainability or expressivity cannot cannot directly tell us which network is good. We have to combine both of them to perform a more accurate evaluation. Okay, so let's dive into the first notion, the trainability. So in our work, we measure the trainability by using the condition number of NTK, and we will show that the condition number of NTK has a quite strong correlation with the network's ground truth accuracy. So here, this is the Jacobian of the network. The subscript I indicates a specific output of the network at the final layer, and the alpha indicates a specific index for the network's parameter. And the NTK, or specifically here, the empirical NTK here is defined by the Jacobian times Jacobian transpose. And the NTK itself is a semi-positive definite and is an n by n matrix. The n here is the number of examples you choose to calculate this NTK matrix. So the more double parameter, the more examples you sampled from the data set, the larger the NTK matrix is. But it is always symmetric and positive definite. So it means that each element in this NTK matrix represents the inner product of the gradients derived by two examples. And recent theory works of the neural architecture deep networks, especially within the NTK regime, tells us that under the linear approximation of the training, the network training dynamics is controlled by the NTK matrix at initialization. So these two equations are quoted from the first reference, and basically it tells us that for the first equation, the on the training set, the output of the networks is governed by the right-hand side. Basically, the exponential over this eta is the learning rate, and this NTK subscribe trend indicates the NTK matrix derived from the training set, and T indicates the training iteration. And if we use the eigen decomposition in this equation, and we can have the second one And this tells us that for each component of the training data set, the training speed or the training process is governed by a specific eigenvalues of the NTK matrix. So from the second equation, we can see that a larger eigenvalue from the NTK matrix indicates that on that specific component of the training set, the network will changes faster during the training iterations. And if we have a very small eigenvalue for some components, basically the output of the network almost does not change through the training epochs. And ideally, we hope the network can learn all the information from the data set, and we don't want a network that can only learn some easy patterns from the data set and just get rid of the hard patterns from the data set. So that means that we hope that different lambda i's can provide us a more balanced training speed during the training for the whole data set. So the idea to use the NTK condition number here to indicate the trainability is that we hope the learning speed of the network on different patterns of the dataset can have a balanced training speed. So we hope that the condition number, which is the lambda max, the lambda 0 indicates the largest eigenvalue of the NTK, and the lambda m indicates the smallest eigenvalue of the NTK. So we hope that this fraction can be small enough so that we can have a more balanced training throughout the training process. And here we try to measure all the condition number of NTK of all the architectures defined in the NAS-Bench-201 because it provides us the ground truth accuracy of all the architectures. And we can see that the smaller condition number almost always indicates a better architecture. And by zooming in the small amount of architectures on the top left, we can see that a small condition number of NTK have a more stable indication of the good architectures. I will pause here for a while and see if there are any questions.
Yeah, I can have a question. Yeah, why in the condition number you could also use, I guess, the average across all eigenvalues, right? So that would be similar pattern, right?
You mean the definition of the condition number?
No. Like, I mean, you could also use, yeah, for instance, the average across all the eigenvalues of the NTK matrix, and that would also be correlated, I guess, with the.
Oh, you mean that instead of using the condition number, you only use the lambda max or the trace or other nuances?
Yeah, the trace, exactly.
Yeah, absolutely, you're right. So we also read other peer works that try to use a trace of the NTK to some paper derive the upper bound of the loss values throughout the training by using the trace of the NTK. So the message is that different usage of the eigenvalues have different indications. So this fraction indicates the divergence of the different speed. And if you are using the trace, you are measuring the average training speed of the different patterns in the data set. And if you are using the lambda max, that means that you only cares about the largest learning speed of the networks regarding the data set. So different spectrum components you are using represents how you define the trainability.
Yeah, makes sense.
So another one too, this is condition number, does it depend on the weights you sample at initialization?
Yeah, exactly.
So how did you do this plot? Because now it's a random plot, right? You average something here, and because inside, I mean, also in the NAS-Bench you don't get the weights, right? So I'm just wondering how. I mean, this is probably an average here.
Right. Yeah, this is a good question. So that's why I said that this NTK is actually the empirical NTK, which means that we have to sample both the examples here and also the initialized weights. So in our work, we did both. So we we repeat for both this plot and the search in the next few slides. We did 3 repeated calculations. In each repetition, we sample a different set of the training data, and also we draw a new random initialization.
And then this is averaged over
Yeah,
these?
yeah, exactly.
Okay.
Yeah. Yes, yes.
Yeah, so also another question that just came to my mind is that for the NTK theory to hold, if I remember correctly, the weights have to be initialized from a certain distribution, right? So
Yeah. Yeah, of course.
do you use that in?
Yeah. We sample it from the Gaussian initialization. Yes.
Yeah, okay, makes sense.
And how large is the data set to compute the condition number?
Here, well, for the whole sample data set, we have the 16 samples for each calculation.
Okay.
So that means that each calculation, our empirical NTK has a shape of 16 by 16.
Okay, and then you sample multiple batches with size 16 to compute the average. Okay.
Yes.
Do you think that would be this number would, or do you think you could reduce the uncertainty if you increase this batch size?
I think it's very heavily depends on the GPU memory you have. So we try different batches and we see that the calculation itself is quite computation consuming. So if you have a very large networks and if you sample a large amount of data, the computation, the memory will the GPU memory will be consumed a lot. So we have to balance the GPU memory you have. So and we find that actually we try different range of the batch size. So we tried from the 8 by 8 to 16 by 16 to 32 by 32, and we also tried the 64 by 64. And the trend here is quite stable. So each calculation may not be exactly the same, but the whole trend that the condition number have a negative strong correlation with accuracy, this trend always hold.
Okay, thank you.
Yeah, no problem.
Okay. Any more questions? Okay.
Well, I guess, sorry, just to follow up on that question, did the correlation get larger with larger batch sizes and it's just more expensive, or did the correlation not get larger?
I don't think it can be, maybe it can be improved a little bit, but not that significant.
Okay, thanks.
Yeah, no problem. Okay, I will continue now. So after this part, the second part is the expressivity. So there actually there are a lot of ways to measure the expressivity of the networks, and there are many old papers that they are all discussing about this problem. And since we are using the ReLU networks for often, and recently there are more papers discussing the specific case that the ReLU networks, how we define the expressivity itself. And here in our work, we leverage the number of linear regions of the networks as a metrics for the expressivity. And we also will show that it has strong correlation with ground truth accuracy. So the reason we can use the number of linear regions for the expressivity is that for the ReLU networks, which means that all the activation functions of the network is a ReLU function. The function itself which maps the input to the output is a piecewise linear function. So that means that given a specific weight and a specific sample, the boundary of the network is a piecewise linear polytope in the input space. And here in this demo plot where the input space only have 2 dimensions, we can see that the mappings from the input to the output is chunked by all different ReLU functions. And for more details, so you're welcome to take a look at the first reference, which has a very clear and good analysis of the linear regions of the networks. Since we in the expressivity, we hope that the network can approximate complex functions, and it's very easy to understand that if we have a very few linear regions chunked by the network, then the function approximated by our network cannot be very complex. The only case that we can make the network chunk the input space into a large amount of linear regions, which means that in each linear region, the function represented by the network is a unique function. In that case, we can hope that the network can learn the complex mapping from your data set to your, for example, for your labels. By referring to the second reference, we use a definition of the linear region as the unique ReLU activation patterns under a given input samples. The reason behind this definition is that given a specific input samples, if we have a large amount of unique ReLU activations, since each concatenation of the ReLU activations represent the affine weights of each affine function which compose the whole network. Then if two ReLU activations are different, that means that these two input examples are located into different linear regions in their input space. So that means that if we have a higher unique ReLU activation number of activation patterns by sampling a given number of input samples, then that means that the networks may very likely have a higher expressivity. And similar to the question from the audience before, the way we calculate the linear region is also the same as similar to the way we calculate the indicator condition number. That means we sample different mini batches and also draw the parameter at initialization for multiple times and average the calculation as our metric. And here we show that the test accuracy, again on the NAS-Bench-201, has high correlation with the number of linear regions. And I'd like to point out that, so in the previous slide, we see that about the absolute value of the correlation is about 0.42. And in these linear regions, we see the correlation about 0.5. So actually, I think that this correlation is quite high because for two reasons. First is that this is not a learning-based method. This is just a analysis and networks initialization. And second is that this does not involve any training. So we purely evaluate the architecture at initialization. So you may see that a more higher correlation in other papers, like the weight sharing papers with some drop paths method or some predictor-based NAS, which could have a higher correlation, like 0.7 or 0.8. I would like to point out that since we are measuring the architecture at initialization, and this is a global correlation, so achieving a correlation around 0.5 is already a quite improvement. Yeah, any questions for this slide? So basically, we will leverage these two metrics to indicate the property of the networks in the later slides.
Yeah, I was just wondering what's happening to the left side points like that. Not in the scatter plot, like
yeah.
large range of test accuracy that have like the similar.
Yeah. That's a great question. We are also curious about this phenomenon, and we find that this whole range of architectures have a similar number of ReLU layers, but they put the ReLU layers in different places. So I think that dramatically differs their test accuracy. For a specific example, we know that the NAS-Bench-201 also includes the zero operator, right? And if we put the zero operator in the upper stream, then it will zero out all the activation in the following following operators, and that means that if we have only one value layers in the cell, we may have the same number of activation functions, but if we put the zeros in the upper stream, then the accuracy of the network cannot be good, because it always zero out the features in the upstream, and the downstream operator always receive a zero tensor. So that architecture cannot be good.
Thanks.
Yeah. Any more questions here?
Maybe one question. So you said you compute this similarly to the NTK, but how do you actually compute the number of the linear region? So you said by sampling, but I didn't fully get that.
Yeah. The reason I said the similar calculation between the two metrics is that they are all empirical numbers, and we have to sample both the mini batches and the network's parameters. That's a similar. That's a similarity between these two calculations. But for this one, actually, I think that the best way to understand is to take a look at our code. So the very easy simple way to explain how we calculate is that we calculate the number of unique value activation patterns by forward certain mini batches through the networks. And some more details is that for example, when we forward a mini batch through the networks, we monitor the activations of all the value layers of all the training examples, and we will collect all the value activations into a whole matrix, and we have a function that to efficiently calculate. For example, we have 100 value layers in the network, and we also sample 100 samples. Then the matrix we will collect is 100 by 100. Basically the 100 samples and the 100 value activations for each sample, and we will calculate how many unique value activations for all these 100 examples. Maybe the unique number of patterns is exactly the 100. That which means that each example here is being placed into a unique linear region, and maybe the unique number of patterns, for example, is like 90. That means that there are some examples are placed in the same linear regions. But you are definitely welcome to take a look at our code, that how to efficiently calculate the unique number of patterns given the collection of the whole bunch of activation values.
Okay, cool. And the uniqueness here is this value on or off, basically, or so it's
sorry,
not.
Sorry, say again.
It's basically, is this value on or off? That's a uniqueness.
Yeah. So
okay,
yeah. So each pattern in my example, I just mentioned, each sample has a vector of size 100 to represent its activation pattern, and each value in the pattern has 0 or 1, right?
Okay, thank you.
Yeah, no problem.
Hey, if the number of value activation patterns is given by if it's a 0 or 1, being on or off, isn't that related also with the weights of the network? And if you are using NAS-Bench-201, you don't have the weight, so the correlation might not be that accurate.
I don't probably I didn't fully understand the question. So you said that the value activation, but after calculating the value activation, we don't need the weights and.
Sorry, I will rephrase. So
yeah.
You check if a value activation, you count the number of linear regions by checking if the value is on or off, right?
Yes.
So isn't a value on or off depending on the weight of the network?
Yeah, of course. It definitely depends on the weights, yes.
So different initializations will give different number of linear regions. So for example, for a specific network, two different weight initializations, you might end up with a large number of linear regions in one and a small in the second initialization, right?
Right. Yeah, it possibly happens, yes.
Okay. So in my perspective, this is very interesting, but there might be an average needed of several weights.
Yeah, exactly. So that's why I said previously that this calculation is also averaged over different sampled mini batches and sampled networks initialization weights.
Okay, thank you very much.
Yeah, no problem. Okay, let's move. And the next question is that a very natural question before I move to the next slide is that since we all see that both two metrics has strong correlation with the test accuracy, so what's the difference between them? So we have to make sure that these two metrics are different notions. Otherwise, we may just need to use just one of them and don't need to use two of them, which will increase our calculation. So we show here that the first one, the first one is the condition number of NTK, and the second one is the linear region of the network. So we show in the plot that these two calculations actually are different notions, and we see that they prefer different operators. So here we see that the blue bars are from the NTK condition number, and the orange ones are from the linear regions. We can see that the NTK condition number prefers more skip connections, which we are known from the ResNet example that some skip connections in the network will avoid the gradient explosion during the training, and will make the training being easier. And the linear regions prefers more the convolution layers, which has more parameters and more ReLU layers, which will increase the network's number of linear regions and will perhaps increase the complexity, the functions that can be represented by the networks. So we can see that these two, although they both have strong correlation with the network's performance, they are selecting different operators and different architectures. So that means that we are not duplicating our calculation by using just two ways, but actually we are selecting different, these two metrics are selecting different aspects of the networks in the search space. Okay, so those are the ways we evaluate the architecture. So we have to find a way to leverage them in our real NAS search problem. And here we will present our TE-NAS, the training-free and label-free efficient NAS. The reason for the training-free is already explained, and for the label-free, since the calculation of the NTK and the linear regions are all getting rid of the labels. So that means that we do not need any labels during this calculation. So that's why our NAS method is label-free. And in our work, we formulate the NAS problem as the pruning approach. So basically, we try to prune the supernet step by step, and eventually we will get a single pass network at the end of the search. And during the pruning process, well, we try to rank the importance of the operators in each pruning step. So very quick collapse of this algorithm is that for each time we try to prune the supernet, we will calculate the importance of each operator, and the importance of the operator is defined by measuring the difference of both the NTK condition number and the number of linear regions before and after removing this operator. So ideally, we hope that by moving a specific operator, we have a larger amount of drop of the NTK condition number. And we hope if the operator is important, we hope that after removing this operator, we also have a large we will have a larger increase of the number of linear regions, or we should minimize the sacrifice of the number of linear regions by removing this operator. And this we combining these two aspects together as the importance of the operator, and we step by step prune the operator by removing those unimportant, less important operators and get a single pass network. So before the next point, I would like to point out that this pruning method is more efficient than the sampling-based method, because if we use a sampling-based narrative search, we can show, which we mentioned in our papers, that the time complexity of the search algorithm itself is is proportional to the power of the choices of in the whole search space. So that means that if we have more choices of operators and we have a more complex edges in the cells, then we have the total complexity of the search is O times the number of operators times the number of edges in your search space. However, in our pruning-based NAS method, the time complexity of the search is number of operators times the number of edges, which is more efficient than the sampling-based NAS. And we can even visualize the search process by using our two training-free indicators. And so here this is the example of the search on the DARTS space actually. And the x-axis is the number of linear regions, and the y-axis is the country number of NDK, and the red numbers indicates the pruning steps. And in each pruning step, we try to prune one operator on each edge in the DARTS space. And the pattern here, we can see that the pruning-based method first try to reduce the NDK condition number, which means that we are increasing the trainability of the supernet, and then we are trying to slightly getting smaller number of linear regions. So the reason behind this pattern is quite easy to understand. So we know that there are many useless or less important operators in the DART space. For example, the zeros and the prunings, and some of the skip connections are redundant actually. So in the first few steps, we are trying to removing those redundant operators that's which will not actually sacrifice any number of linear regions, but actually can help to improve the trainability of the networks. And since the target of the neural search on the DART space is to select a single pass network from the search space. So that means after removing all those redundant operators, we have to sacrifice the linear regions to remove some of the other redundant operators. So that's why we see the slightly drop the linear region. That is because for example, there are two operators, operator A and B. They both have high expressivity, but we have to choose one of them on this edge, which is required by the DART space. So that's why we have to sacrifice some of the linear regions. So this is try to understand the whole search process.
Quick question. So
yeah.
Since you're pruning the space, why are you using also the zero up in this space in the first place?
You mean why we are still using the zero operator?
Yeah, I guess you can already remove that. Don't include in the space, right? Since you're pruning that iteratively.
You can remove it. So but whether to remove or not to remove it do not have effects on our calculation. So even if you have zero operator in your search space, you can still calculate the condition number and the linear regions of the network. So you can it is okay to remove it. Yes.
Mm-hmm. Okay.
So that's most of our methods, and for the final evaluation, we are targeting on both the performance of the search and also the search time cost. So we see that first, since our method does not involve any training, our search speed is quite fast. So on both some tiny benchmarks and on the more complex DART search space, the training time cost of our method is always the top first in all the methods. And on the NAS-Bench-201, there is also at the publication time, there is also another peer work called the NAS without training. So their method is even faster than ours. I guess that this sampling quite fewer samples in their calculation, and we can see that their performance has a large gap between ours. So that means that our method has a much better trade-off between the search cost and the performance. Yeah, I think that's all my presentation, and I can take more questions. Thank you very much, and you are very welcome to take a look at more details in our paper and our code. How did we implement that? Thank you very much.